Hello everyone, I hope everybody's fine and ready to learn other formulas for limits. This time we are discussing trigonometric limits, and I have a diagram here. This is a unit circle whose equation is x squared plus y squared equals 1. And in this unit circle we have an angle theta in the first quadrant, which makes a sector actually. So OAD is actually called a sector of a circle, just like slice of a pizza. So this is the diagram right here. This is a sector OAB, which has the central angle of theta, and it has a radius of r. And in fact, the formula for the sector of the area of any sector is 1/2 r squared theta. So you multiply 1/2 by the square of the radius, whatever it is, and then you multiply it by the measure of the central angle in the sector. But you have to be careful that this angle has to be in radian. It cannot be in degrees. For example, if it's 30 degrees, you should write pi over 6 radian, not 30 degrees. If you plug in 30, it will be wrong. So that's just a brief explanation about how we find the area of a sector. So here we have sector OAD, okay, which is created automatically when you draw this radius OA in the circle and you separate angle theta at this corner. So a sector like that is obviously generated. And then if you drop a perpendicular from point A, where the radius intersects the circumference of the circle, then you also generate a right angle triangle, which is triangle OAB. That's a right angle triangle that is generated by dropping a perpendicular from point A. And if you start from point B, which is the foot of the altitude, if you start from point B and you draw another arc which intersects radius OA at point E, you are generating a small actually sector here. So that small sector would be OAB, sector OEB would be that small sector that would be generated. And then we have right angle triangle OAB, and then we were going to have the big sector OAD, of course. Okay, so there's three areas involved here. So it's needless to say that both big and small sectors have the same central angle of theta. Now, it's not a secret to mention that the area of the sector OBE, which is this small slice of pizza, is less than or equal to the area of triangle OAB, which obviously the area of the triangle is larger. And then it's less than or equal to the area of the sector OAD, which is the biggest slice of pizza we have here, the biggest sector basically. It's needless to say that. And mind you that this angle theta could be like any angle. It could be like 30 degrees, 40 degrees, 45 degrees, 10 degrees, even 2 degrees, that doesn't matter. But in anyhow, whatever angle that is, we are going to say this inequality is valid and true, as you see in the diagram. Now, the question is, how do you find the area of sector OBE? Well, we are going to use the formula that we discussed. It's going to be 1/2 times the radius, which is OB, okay, and then times, of course, OB squared, and then times the angle theta. So that's going to be how you find the area of sector OBE. The area of triangle OAB is like very easy based on side divided by 2. So it's going to be 1/2 times OB, which is the base, times AB, which is the height. And then for the sector OAD, we can say it is actually 1/2 times OD, which is the radius of the big sector, squared according to the formula, times, of course, theta again. That's what we can say. Okay, so this much we say. Now, we see that the fraction 1/2 is common here, so we're going to multiply all sides by 2 to get rid of those fractions first of all. So it's going to be OB squared, okay, times theta, and then we're going to have OB times AB, and we are going to have OD squared, which is actually 1 squared, because you know that this is a unit circle, so the radius would be 1 squared times theta. All right. Now, about OB and AB, what we can say, well, if you remember, I said that this is a unit circle, so that means that the hypotenuse OA of the right angle triangle is actually the radius of the circle, which happens to be 1. So I can say OA is the hypotenuse of the right angle triangle, and that is equal to the radius of the circle, which is equal to 1, because it's a unit circle at the end of the day. And if that is the case, then in that case, I can say that OB is actually the adjacent side to angle theta, and because the hypotenuse is 1, so adjacent over hypotenuse would be just adjacent side itself. So that means that this is actually cos of theta, because cosine of theta is basically OB over OA. I can't even write it down. I can say this is OB over OA, but the thing is that OA is equal to 1. Therefore, if we say OB is cos theta, it makes sense. And similarly, we can say that the opposite side to angle theta, AB, is actually sine of theta, because sine is defined as the ratio of opposite side, AB, over hypotenuse, OA, but we said that the hypotenuse is actually equal to 1. So having said that, instead of OB, I can write cos theta, and instead of AB, I can write sine theta. So that's the substitution I can do here, and 1/2, as I said, it's already gone. Now, I'm going to divide all 3 sides by angle theta. So this would be OB squared. This would be cos theta, sine theta divided by theta. And this would be just theta divided by theta. All right. And here, let's say theta divided by theta. So dividing all sides by theta. Simplifying, the right side would be 1. The left side would be cos theta times sine theta over theta, and the left side would be OB squared, which we said is cos squared of theta. So cos squared of theta. Now we divide all 3 sides by cosine of theta. So we end up with cos theta on the left, and this would be sine theta over theta, and this would be 1 over cosine of theta. So after dividing all 3 sides by cos theta, this is what we end up with. And now we are going to say, okay, we're going to say, what is the limit of cos theta when theta approaches 0? That's what we are asking ourselves. And it's needless to say that cosine of 0 is 1, obviously, so direct substitution method would work. And even if not, you can draw the graph of cosine function, and you see that, let me graph it for you. The graph of cosine function is something like this, obviously, right? So if x approaches 0, even from right side or from left side, it doesn't matter, because the max value is 1, and the limit of cos theta would equal to 1 when theta approaches 0. So this is like a fact. And for the same reason, if I take the limit of 1 over cos theta on the right-hand side when theta approaches 0, because the denominator approaches 1, and then 1 over 1 would approach 1, obviously. So again, limit is 1. So what I showed is that the limit of the function on the left is equal to 1. The limit of the function on the right is also 1. So let me write this down, actually. So I'm going to say limit of cos theta is equal to limit of 1 over cos theta when theta approaches 0. And we said that this is actually equal to 0, actually equal to 1, sorry. Is actually equal to 1. So this is what we said. And on the other hand, we're saying that these 2 functions are in a way that a third function, sine theta over theta, is actually squeezed in between, or sandwiched in between. So using the squeeze theorem in calculus, we can say if we have a function like sine theta over theta, which is actually in between the 2 other functions, cos theta and 1 over cos theta, and the limits of cos theta and 1 over cos theta are both equal to one another, they're both equal to 1. According to the squeeze theorem, we can conclude, we can say, therefore, limit of sine theta over theta, which is that function which is squeezed in between these two functions, when theta approaches 0, must also be equal to 1. That's the conclusion that we can make here. And as I said, it doesn't matter if theta approaches 0 from right side or left side, because you saw what happened in the cosine function limit. If this is cos x, and you're finding limit of cos x when x approaches 0 from right side, that is actually the same as the limit of cos x when x approaches 0 from left side. They're both equal to 1, it doesn't matter. So here, it doesn't matter if x approaches 0 from right side or left side. This limit is going to be 1 anyway. So I'm going to write down here the conclusion we wanted to come up with. Limit of sine theta over theta when theta approaches 0 is always equal to 1. And today we actually proved it. This is a geometric proof of why this is true. And this is like a very, very fundamental formula in trigonometric limits. And I should confess that there is almost no limit question that you solve without using this formula. It's that fundamental. Any complicated limit, trigonometric limit you want to find, one way or another, at some point, you see that you have to refer to this very famous, important formula that we concluded today. So remember, limit of sine theta over theta when theta approaches 0 is equal to 1. That's what we proved today. In the next lectures, I'm going to give you a variety of examples of trigonometric limits. And if I refer to this formula in those complicated trigonometric limits, then of course I can do that because we just proved it together. Thanks to Squeeze theorem, of course. Thank you for your attention, and we'll see you again